Good afternoon to all of you. Myself, Anil Kumar, and I am here to take one lecture on image classification techniques under course Remote Sensing and Digital Image Processing, which has started on 22nd of August. I hope my PPT and voice is coming. Please confirm. So here, if you see image classification techniques, which is we are using remote sensing images. So remote sensing images has very strong application for preparing thematic map. And when we want to prepare thematic map, we can go for visual interpretation. Visually, we can prepare the map, but that is time consuming and lot of effort is required, lot of manpower is required to digitize the different features. But second is digitally we can classify and we can prepare the thematic map. So here the focus will be on digital image classification for remote sensing images. So before I start the image classification techniques, we have to understand what is image again, so that you get focused that how different classification algorithm works. So here you can see the topic under DIP, what I'm going to cover. One is separability analysis I will focus, which is very important before we consider any multispectral image to be used for classification. Then actually we will go for image classification approach, then accuracy assessment. So these are the three broad topics which I'm going to cover in my today's lecture. So before we go further, we have to talk about what is image. This is very important to understand. So here, as I mentioned, that I'm talking about to understand what is image. That is very important. So here, if you see, this looks to be an image as a very beautiful rosebud. And here also, this is a very good image. And then this one, so funny and so beautiful kid is also an image. And this also looks to be very good image. But we have to understand to define mathematically what is image. Why? Because we want to process these images. And if you talk about say remote sensing image, this is a remote sensing image, sea area and the land area. If we see this small area like this here and here you can see the image in the form of grid, like some gray, white or black or dark gray color grids. These are called pixels. And if you zoom further, you will see here numbers. So here basically what is happening, the image is in the form of rows and column, and the smallest unit is pixel, and here the pixel has digital number. So what we do in digital image classification, we try to group these pixels which are similar in nature. So image, when we see, this is not actually image, we have to see for image processing point of view. This is basically actual image, because processing means we are manipulating the image pixel values. Next, we can understand a little bit about multispectral image. So from multispectral camera, we may get 7 bands, like for Landsat images like band 1, band 2, 3, 4, 5, 6 and 7. And then if you take any of these random bands, of different bands, you can pass on to some primary guns, that is red gun, green gun and blue gun. So you have tinted outputs you get. This is red tinted, green one and the blue one. And if you superimpose all three, you get a false color composite. So here this is just understanding how the false color composite comes. So in the false color composite, we can use maximum 3 bands, not more than 3. But total you can see here there are 7 bands. So this you have to also understand when we are trying to visualize the ground through these images. maximum we can take 3 images when we go for false color composite. So here when we move further towards classification, basically we are trying to apply the concept of pattern recognition. So what is pattern recognition? So it is pattern plus recognition. So first thing is on the image we can see some systematic patterns or some irregular patterns like this one or this one. So third one, what we see here, this is temporal pattern you have. It's very funny, but this is very, very important to understand that sometimes in some applications we can use the temporal pattern also. And then you can have some natural random patterns like pattern of clouds in the sky. And if you take some digital elevation model, you can have some natural streams. So they are also showing some natural patterns in these derivatives of the DM. And pattern you can see in the text form also to recognize. So the data can be from different form, and there you can see the patterns where we think to apply the pattern recognition techniques. This can be like recognition of face in a video camera, or in the remote sensing we see there are patterns of different classes like AWIPS image at 60 meter, same area at 23.5 and same area at 5.8 meter pixel size. So we can see some patterns how it is changing here. This area looks to be at 60 meter like this. Same area you can see how it is appearing at 23.5 and same area you can see how it is appearing at 5.8 meters. So here when we talk about pattern, we have to create some signatures for each class. When we apply these signatures, we can use it for recognition purpose and classify the patterns as per the signature data we have provided. We have to also understand the image properties or image information content, which is very, very important and which is defined by resolution. So there are different type of resolutions which are affecting the image classification. So first one, what we see is the spatial resolution of the image. You can see the same area at 2 meter, then 1 meter and 0.5 meter in different locations, how it is appearing at 2 meter, then 1 meter and 0.5 meter. Here also 2 meter, 1 meter and 0.5 meter. Same way here, this one 2 meter, pixel size 1 meter and 0.5 meter, and same way this one. So accordingly, we are using the image of different resolution. We have to select the image as per our application. What size of object we are looking to be captured by the image and to be extracted. Accordingly, we have to decide the spatial resolution of the image. Second, here you can see the again effect of spatial resolution, very low resolution of spatial, then medium and high resolution. And you can see how the information content changes from low to medium to high spatial resolution. Second is spectral resolution. Spectral means resolution means to distinguish, and spectral means with respect to wavelength. So if you focus, suppose this area, this looks to be gray in band 1, in band 2 it is little dark black, and it is more dark black, and finally very dark black. So it is changing the same area as per the band. So you can distinguish the same area with respect to band combination. It has very, very important application like deciduous and coniferous trees to distinguish, or coastal area with water and sand area you want to distinguish. Third is radiometry. That means how many shades are present, and radiometry is represented in the form of bits. What's the bit of the image? 8-bit or 9-bit, 10-bit like that. So here one image you can see it has less radiometric resolution, and here you can see more radiometric resolution. Basically here you can see less shades, and here you can see more shades. So once the radiometric resolution is more, you can have again much shades of the object. Fourth one is temporal resolution. There are satellites presently available which gives you image of 16 days. Every 16 days one image. So you can see the changes coming up. due to some flood area. In this area, it is not flooded, and here after some time it is flooded. So you can capture this area depending upon the temporal frequency of the data available for the same area. Landsat give you 16 days data. If you take Sentinel-2A and 2B satellite combination, within 5 days you can get the data. But if you use only one Sentinel-2 satellite, then it is available every 10 days at 10 meter. Third, very beautiful satellite data available is from PlanetScope Dove satellites, where there are 130 satellites plus available in the space. And these satellites can provide you today as a 8-band 3-meter data every day. For research point of view, you can use it and download and use it. So further now, moving to the image classification concepts. Before that, we have to understand how to visualize my data. One is we can visualize the area like this using the false color composite, and we can visualize my area, how the area looks, what are the different objects present on the ground. Second is we can visualize in the feature space like here band 1, B1, and this is your B2, and this is your B3. So this bands combination, you can see maximum 3 axes, and you can plot the band values, and you can see this can be settlement, this can be agriculture, this can be forest, water body, and so forth. So you can have the clusters of these classes objects which are present on the ground, and you can visualize how this data is coming for different classes. So here this is called feature space, and in the feature space, if you can find out any point and you draw a vector, that becomes feature vector. So here this has the direction and the distance. The very important point coming out for image classification is separability analysis. So when we use multispectral image for thematic map preparation, and nowadays you are getting 12 to 13 bands in the multispectral domain. So if I'm expecting forest class, water class, then built up class, then agriculture class, like this. So we have to see that do we have to use all the 12 bands available in the data, or just 4 or 5 or 6 bands are okay. So how to know the answer of this, that how many bands are sufficient to be considered to map the classes which I'm looking for, like forest, water, then built up and agriculture. So what are the bands? So for that we can get the answer from separability analysis. So what the separability analysis does, quantitatively it selects which subset of bands or features. Here you should understand, in the multispectral image all bands are also called as features. So separability analysis quantitatively tells subset of bands or features provides the greatest degree of statistical separability between different classes. Classification means we should have sufficient distance between classes so that algorithm classify all the classes very nicely. So we have to see what is the band combinations I should select from my given input data, which can give the greatest degree of statistical separability. So that is a use of separability analysis. So here it is basically discrimination technique that allows separation of major land cover categories with a minimum of error and a minimum of number of bands. So it basically discriminates between classes while considering minimum number of bands. So here how it works on the training data. So for each class we have to generate the training data, and on the using this training data we can find out what are the bands to be required to find out the minimum number of bands in my data. And basically the algorithms developed, they follow the concept of normally distributed. That means my all data should be normally distributed, and then we can apply some algorithms to find out what are the minimum number of bands required to classify the image and giving the maximum separation between classes. So here, if you talk about separability analysis, there are a few methods in the literature. One is transformed divergence, and second is Jeffreys Matsushita distance equation. So these are two mathematical methods, and third one is graphical method. So I will talk about all. So if you talk about here separability analysis with the graphical method, graphical means you can draw the maximum three axes, B1, B2, and this is your B3. So here, if I plot any selective band which I'm looking for, so I can see how the forest is plotted, how the water pixels are plotted, and how agricultural lands are plotted. So we can see how nicely the separation is. So this is a graphical method. Maximum we can consider three bands, because maximum we have three-dimensional, three axes only. So at each axis we can plot one band data, and we can see how the separation is coming out between these pixels of different classes. But maximum here we can use only three bands. Second is here. So this was the graphical method, and second is by statistical methods. If we see, one is transform divergence using mean and covariance matrix. So here we have to calculate divergence between two classes, for example, C and D, and we can find out here this is your variance and this is your mean value. And if we use the variance and mean value, we can find out divergence, and divergence we can use in this formula to get a transformed divergence. So here the value comes 0 to 2000. So if value is around 2000, it is very good separation. If it is 1900 and above, it is good. It is good separation. And if it is less than 1700, then it is poor separation between classes. So we should consider that the here the transform divergence should be near to 2000, so that we have excellent separation between classes. Second method is so here you can see for 2000 this is excellent class separation. Above 1900 it is good separation. Below 1700 is poor separation. Second is Jeffrey Matsushita distance. Here the data should be Gaussian in nature, that means normal distribution, removal of least effective features, and transform the pixel vector into a new set of coordinates in which least effective were removed, right? So this way here, if you see, it is again using mean and variance covariance of two classes. It is calculating the Bhatt parameter between C and D classes. Using Bhatt parameter here, we can get the Jeffrey Matsushita distance. Again, as per the value of Jeffrey Matsushita distance, we can understand how much is the separation between classes. So here just I talked about introduction of image. Mathematically, it is a row and column and having the pixel value about the image to understand mathematically, and then I moved further to separability analysis and its importance, so that we can find out the minimum number of bands in a given image to be considered for mapping the given number of classes. Next, coming to digital image classification. So the objective of this operation in digital image processing is to replace visual analysis of the image data with quantitative techniques for automating the identification of features in a scene or in an image. Here you can see if it is a 5-band image, if I do image classification, I can group the pixels into different classes. Like some pixels can be labeled 1. 1 means water. Some pixels are labeled 2, that means vegetation. Some pixels are labeled to class is 3. 3 which are basically wetlands, and some pixels are labeled to soil, that is class soil here, right? Now the classifiers which I'm going to talk about is pixel based classifier. I'm going to talk pixel based means they are using the pixel information. That is the pixel value they are using. That's why they are called pixel based classifier, but they are also called parametric. Parametric means there is no coefficients present in this very basic statistical classifier, and you can just give the input data. You get the standard output data. There is not much variation always. If you change the algorithm or the data output will remain same. That's the meaning of parametric. No extra coefficients are used to be optimized. So these are also called statistical classifiers. So they are pixel based classifier and they are parametric classifier, and they're also called statistical classifier because they are using the statistical parameter like mean, variance, covariance, minimum and maximum parameter, and say standard deviation. So these are the mainly parameters these algorithms use, and that's why they are also called statistical classifiers. So as per the subcategory, I can list some of the algorithm under unsupervised classification approach. The very basic algorithm is used, that is C means. It is also called K means also. In supervised classification algorithm, the basic statistical these algorithms are, which are pixel based parametric statistical classifier like minimum distance classification, that is C means. Then Mahalanobis classifier. Then just a minute. Sorry, there was some call. So I was talking about the list of supervised classifier like minimum distance classifier, then maximum likelihood, then Mahalanobis classifier, then parallelopiped and boxed classifier, and finally the maximum likelihood classifier. So these are all supervised classifiers under pixel based parametric and statistical classifier category. So we'll take first the unsupervised approach. And also I will cover in the last the classification accuracy of the thematic map which we generate through these approaches. So in unsupervised means we take some image and we group the pixels into clusters. Cluster 1, cluster 2, cluster 3, cluster 4. So whatever classifier we apply, we are not providing any extra data to this algorithm. We are just taking the basic image and grouping the pixels into different clusters. What is happening here in the output, there is no name of the class. So we are just putting the label as C1, C2, C3. I do not know what is the label. Is it water or forest, which I do not know because there is no training data. So in unsupervised, we don't provide any training data, and algorithm does iterations, and as per the iteration, it divides the pixels into different classes. I can explain you mathematically how it works in the next slide. Let's take this one. So here we can just take it, say 2-band image. Suppose this is a 2-band image I'm taking. Now what I do, I plot these 2 bands on X and Y axis. So this is my X axis, which I'm plotting here, band 1. And this is your Y axis for B2, right? So here we can see the pixel locations, pixels plotted in this feature space. So this is my feature space. So all pixels are plotted in this area, in this feature space. So if I'm going for unsupervised, that means I'm using very basic algorithm, that is C means. And in C means it is using the distance equation. So I can write the Euclidean distance, d square I j x1 minus x2 square plus y1 minus y2 square. So here the distance has been calculated. So here this is the pixel coming from band 1. This from your band 2, and then again y1 and y2, right? So this is your band 1 unknown pixel, and this is the mean from band 1, and this is the band 2 unknown pixel, and this is the mean from band 2. So here I can write bar, that is mean value I'm taking for equilibrium distance. But the problem here is we don't have training data, so we have to provide some secondary data, like how many clusters we want to generate. So we have to tell, suppose C is equal to 2, right? And we have also to define the number of iterations, because this algorithm has to iterate. It's just like you can understand in a class, if the teacher is teaching, then it is supervised class. But when the teacher is not there, he comes and he gives just 10 questions to the students and went off from the class, then class is unsupervised. So the students has to get the answer of the these 10 questions by themselves, which takes time. Initially, they understand the question and get the answer by themselves. They are not satisfied, so they ask to their friend. Then third time they are still not satisfied. They ask, or they search on the Google Earth, or they are not still satisfied. They see the concerned book. And again, so they are doing iteration, initially asking by the understanding by themselves, then asking with the friend, seeing on the internet, and then reading the book. So they are using different sources every time, and they are trying to define the answer of that question. But when the teacher is there, in the single step, teacher tells what is the question, what is the answer of the question. So that's the difference between supervised and unsupervised class. Same way here. In the algorithm, there is no training data. We have only the input image, and they want to divide the pixels into different groups. So they have to tell some of the things like how many clusters you want and what is the iteration it should be. And third one, more parameter, we can give the error acceptable error delta naught. Suppose 0.9. So here iteration will stop if any of these two conditions are true. So I'm putting OR condition. If this is true or this is true, algorithm will stop training and start dividing the data. And we can tell how many clusters we want. Suppose we want 2 clusters. So once we say we want 2 clusters, we have to basically generate the mean parameter randomly for cluster 1. Suppose x bar 1, x bar 2 here. And same way here we have to tell y bar 2 for second cluster rather, because we don't have label. So I do not know what is class 1 and class 2, its label. So I can here be in unsupervised, we talk about cluster 1 and cluster 2. So once this is given, it will the question is that algorithm has to find out this pixel belongs to cluster 1 or cluster 2. So it will use this distance equation and find out the distance for with respect to mean of first cluster and then mean of second cluster. And whichever is minimum, the label will coming up. If this minimum to cluster 2, it is labeled here to class 1. So this is my class 1 for X and class 2 is for Y. Same way, if I see this pixel, it is what is it for class 1 and class 2, X and Y. So this is now minimum for Y, this becomes class 2. So like this, we can go on labeling. So what will happen? A few clusters, few pixels will come to cluster 1 and few pixels will come to cluster 2. So whatever pixels we got in cluster 1, we can use that pixels and to find out the new mean. And same way for here, we can find out the new mean here. Assumed, and that may not be correct. So after first iteration, we got the new mean. Using this new mean, so again, we can divide all data to come to cluster 1 or cluster 2. So once it is done, again, we can find out the new mean X bar 3 and Y bar 3. Like that, we can proceed. And like this, we can go on. And then here, what is happening? The mean is changing. The mean was here. The mean has came somewhere here. You can find out the distance. And here also you can find out the distance. And if you take the average and you can compare, the average delta is smaller than delta naught or equal to or not. If it is bigger than, it will not stop. This condition is not true. And iteration is also not true because iteration is done only once. Same way you can do second iteration and you can see the mean is shifting here, and this mean is also shifting. You can find out the mean shift error, and that error, if it is smaller than this, it will stop. If it is not true, it will not stop. So it will go on doing it iterations number of time till any of this condition is true. And once this condition is true, algorithm will stop. So in each cluster, you will get few pixels here. So this way this works. Here, the very important thing has been seen. The algorithm has been selected such a way for unsupervised classification that its parameters are very simple to estimate or to refine or to assume. So here it is using only mean parameter, which is very easy to assume and refine it. That's why in unsupervised approach, we use very simplest algorithm like C-means. So here you can see the example of C-means algorithm. It is basically finding out this pixel belongs to this or not. For this pixel here, the distance is minimum. So here it is labeled to class B, not the class A, because here the distance is more. This is the Euclidean norm. When we are using the normal distance equation, that is the Euclidean distance. It is using only the mean parameter in the algorithm. We can also apply the Mahalanobis one, but in the case of Mahalanobis, we are using the mean as well as covariance from the data. But since we don't have training data, so we cannot use Mahalanobis distance because the covariance is very complicated parameter to be estimated and to be assumed. Anyway, coming to next type of classification, that is supervised in the same domain, supervised classification. So this is very simple one. So here the difference between with unsupervised is here we provide the training data. So we know that we are dividing the data into three classes, that is water, agriculture and rock. So we are providing the training data of water, training data of agriculture and training data of rock to this image and to this classifier. So once we apply the input image of 3 band and the training data of 3 classes, we can get the output as this area is class A, that is water. This area is class B, that is agriculture, and this area is class C, that is rock. So in single iteration or single classification step, we can get the thematic map with label. So pixels are grouped and we can see label also. But in unsupervised, the label is missing because we are not provided training data, and that's why label information did not came to the algorithm. So these are the algorithms in supervised classification: minimum distance classification, Mahalanobis distance, parallel piped, and maximum likelihood. So we can understand these algorithms mathematically in this slide. So here, if I take 2 band data, and we can plot the band 1 here and band 2 here. So if you take the first one, minimum distance classifier, that is C-means algorithm only, it is using only the mean parameter. So for that, it calculates the distance ij, I is input pixel and j is the class. So here it will have the distance like x1 minus x2 bar plus y1 minus y2 bar square. Right. So here this is the unknown pixel vector, and this is the known mean of the class. So here I is the pixel and j is class. So if j is equal to 1, that means it is a class 1, say water, and if j is equal to 2, then it is class agriculture. Like that we can go. So here we have to collect the training data of each class, and once we collect the training data, since we are using here C-means algorithm for supervised approach, so it will generate only the mean parameter from each training data. We may have training data of water, we may have samples of agriculture, and we may have samples of forest. So from these samples, we can find out mean for water, mean for agriculture, and mean for forest. Using these mean values in this equation, we can find out the distances for each unknown pixel. So whichever the pixel gives the minimum distance for a particular class, so that pixel is labeled to that class. So in single iteration, we can divide the image into output as a thematic output. Second is Mahalanobis distance. So what is the difference between Mahalanobis distance and the C means? It is using only mean. The Mahalanobis distance use mean as well as variance covariance. So here, if you see the distance formula, distance square comes to be like that: x1 minus x2 transpose, and then A inverse, and then x1 minus x2. So here x1 is the unknown vector, x2 is the mean vector, x2 bar we can say. This is the mean vector. So here this is the vector difference, and we have taken the transpose of that difference. AI is the weighted matrix. This can have three forms: unit matrix, variance covariance norm, and diagonal variance covariance norm. In the software, you will see they are using only variance covariance with mean, but you can have unit matrix also. If you use unit matrix, this becomes like a equilibrium distance. And if you are using diagonal variance covariance, you can take that also, which is equivalent to more or less Mahalanobis distance with a diagonal norm of variance covariance. So here the difference is in Mahalanobis distance, we are using the mean and variance covariance. So that is the only difference. Rest, it is working with minimum distance approach. And for each given pixel, whichever is minimum distance, it will label that pixel to that class. Third one is parallel piped or box classifier. So here a parallel piped and box classifier, how it works. It basically, again, if you take the two band feature space, it creates the box. So how it will create if we provide the training data of water, and it is two bands, sample one, suppose it is 20, 30, second sample 22 and 33, third sample 25 and say 29. So then we can find out from the samples the mean parameter, and we can also find out the with respect to mean with sigma value in band 1 and in band 2. Second variables, we can calculate the minimum in band 1 and band 2 and plus maximum in band 1 and band 2. So there are two methods through which we can create a box. So if I'm using mean and sigma variation, that's standard deviation. So mean for class 1 is here. So I'm showing you how to create the box for each class. So mean is here. So this is your minus sigma and this is your plus sigma. Same way here, you have a mean here, then minus sigma and then plus sigma. So if you connect and these lines here and here and here, so you got this box. So this box is your class water. Same way you can take the mean and standard deviation for agriculture. You can get a box for agriculture. You can take the minimum and maximum concept. So here you have a minimum, you have a maximum. Same way you have a minimum and maximum. And if you connect them, you got the box. So this your box came up. So you can take any of these parameters, either mean and standard deviation or minimum and maximum, parameters to create the box. And once you create the boxes for all the classes, so whatever pixels comes in that box, they are labeled to that class. So whatever pixels are here, they are labeled to water. Whatever pixels are here, they are labeled to agriculture. So like this, you can create the boxes and classify the pixels. So this is very quick method, but this does not give you so much good accuracy. Next is MLC, maximum likelihood classifier. So here in MLC, we create the probability function P is equal to 1 upon 2 pi to the power n determinant of weighted matrix A inverse into minus 0.5 x1 minus x2 bar A inverse and then into x1 minus x2. This is bar mean, and here there is a transpose. So this is a simple same distance equation for with Mahalanobis. So here n is the band. So here this is band of the image, and here this is the weighted matrix. This is your mean of a class. So once you get the probability, suppose you are dividing the data into water and agriculture. So you can find out for each pixel the water probability, and you can find out the probability for agriculture. So whichever is maximum for each pixel, that pixel is labeled to that class. So here it is maximum, and in the distance concept that should be minimum. So that way you can divide all the pixels into different classes. So here you should note down that the algorithm is using mean parameter as well as this A inverse will have 3 norms as in Mahalanobis: equality norm, variance covariance norm, and diagonal variance covariance. In the software and the book, they generally talk about it is a variance covariance norm, but in the literature, in the research paper, you can see people have mentioned we can use it equilibrium distance here. We can use variance covariance, or we can use diagonal variance covariance. I also use in my PhD the different concepts and studied how they are behaving. So here, but in the commercial software, you see only the probabilities using mean and variance covariance matrix. Coming to next part of image accuracy assessment. So here you can see that once we create the thematic map through these digital image classification, suppose this is your thematic map. Which shows this is water, this is agriculture, and this is your forest class. So you should know the overall accuracy also of this thematic map. So for that, there are methods, well-established standard methods for this algorithm, that is error matrix or confusion matrix. So for that, we require some reference map also, right? So this is your classified map. And now we require some reference map as a ground truth testing data. So here it talks about that this is your water class, this is your agriculture class, and this is your forest. So from reference map, we can check the accuracy of our classified map. So how it works, we have to take here testing samples. Testing sample. So if I take first sample in the classified, this is water. In the reference also, this is water. So this way we can create here. If I take here a matrix of 3 by 3, if there are 3 classes, I can have 3 columns and 3 rows. So this is your reference map information, and here this is your classified information. So as I told you in this example, first sample, testing sample is water in both the cases. So I can say A is water. So here is also water in the classified map, and the reference map is also water. So here I can add 1. Next sample I take here. Here it is agriculture in the classified image, but here it is water. So water is class 1 and agriculture is class 2, for example. So 2 means B. So here in the classified map, this was agriculture and the reference map was water. So reference map was A and classified map was B. So the sample will come here. Testing sample will come here. Then if I take third sample, this is agriculture and this is also agriculture. That is BB class in both the maps. So B means here it is again B and here also B. Sample comes here. Third one here, if I see this sample here, this is agriculture and here it is forest. Forest is C class. So on classified it is agriculture, that is B, and on the reference it is C. So B and C it comes here. So like this you can go on adding. If sample comes here again after a few times, so you can say 1 plus 1 it becomes 2. So you can go on adding up. So here I have already created the confusion matrix or error matrix with few number of samples while taking 3 classes A, B, C on the reference map and A, B, C on the thematic map. So after adding all the testing samples, I got 35 samples as class A on the reference and classified map. 2 number of samples on reference, but on the classified it is for A. Like that, and for 2 number of samples for class C on the reference map, but on the classified it is A class. And here it is your row total for each class, and here it is your column total. So this we can find out. So once we get these parameters, and if you sum up these values and these values, you will get 136 here. So 136 are basically total number of samples. Total number of testing samples. Testing samples. Now overall accuracy, we can now find out so many parameters from this error matrix once it is generated using these classified map and the thematic and the reference map. Once this error matrix is generated for all number of classes, we can calculate few parameters. First is user accuracy. User accuracy means how correctly my testing sample are on the classified image. Please remember the definition of user accuracy. User accuracy means how correctly the sample is classified on the classified map. And then, so here for class B, here you can see on the thematic map, and here also on the reference map, it is 37 samples has been correctly marked on the classified map, but total number of samples were 50 on the classified map. So here the user accuracy will be 37 divided by 50 and multiply by 100, it is 74. If you take the difference with the 100, this user accuracy, then you get the error of commission. So this is 100 minus user accuracy. So it comes here 26 for class B. Same way for producer accuracy, the definition is it tells about how correctly my testing samples are on the reference map. So I'm repeating again the definition of producer accuracy, how correctly my samples are identified correctly on the reference map. So here the total number of samples correctly marked on both the maps were 37 for class B, and on the ground truth, that's my reference map, is total number of samples were 40. So you can see the accuracy is 37 by 40, it is 93. And with this you can also find out error of omission, it is 100 minus producer accuracy for class B, and it is 7%. It's 100 minus producer accuracy, that is 93. So it is 100 minus 93, it is 7%. So for all the classes, we can find out user accuracy, and for all the classes, we can find out the producer accuracy. Next is overall accuracy. How to find out overall accuracy? So for overall accuracy, we have to find out the diagonal sum. So here, if you see the diagonal sum, it is 35 plus 37 plus 41 divided by total number of samples I have mentioned you. If you find out row total or column total, it is 136. And multiply by here 100 so that you get a percentage. So like this, you can find out overall accuracy of your thematic map. And the fourth parameter is kappa coefficient. So kappa coefficient you can calculate from this formula, and the variables I can explain. N is total number of samples. So that is 136. So here N is total number of samples, that is 136. Xk plus 1 is your row total, and X plus K is column total for particular class. So here you can find out it is for first class row total and column total is 30 into 50. So here I can just type the variable summation X plus K and plus K X. So here this will be in first 39 into 50. 39 into 50 plus for second class it is 50 into 40. 50 into 40. And for third class it is 47 into 46. Yeah. 47 plus 47 into 46. So this you can now find out, and N square you can find out. This you can again find out here, right? So if you put, and this summation KK is the diagonal sum. Summation, that was XKK. X KK, this is your diagonal sum, right? That was 35, 37, 41. 35, 37 plus 41. So once these all the variables are known to you, if you put up here, you can get the kappa coefficient. This will go 0 to 1 value. This is not in percentage. It will be in decimals, 0.1, 0.2, like that, 0.8, 0.9. So kappa should be tending to 1, right? So here if you see kappa is, if it is more than 0.8, it is excellent. If it is 0.6 to 0.8, very good. If it is 0.5 to 0.6, then it is not even good, it is fair. And if it is less than 0.5, then it is poor classification. So these are interpretation, same interpretation you can see for overall accuracy. For overall accuracy, if it is more than 80%, then it is excellent. If it is 60 to 80, then it is very good. If it is say 50 to 60, then it is fair. And if it is less than 50, then it is poor. So this way the interpretation is done for the classified map to be, which has been assessed with these parameters. It has been noticed that the overall accuracy is using only the diagonal elements. Here you can see. So overall accuracy is using only diagonal elements. It is not considering the off diagonal elements of this matrix. So number of times people does not consider that overall accuracy is very good parameter. But kappa coefficient is using all the parameters of this matrix, diagonal and off diagonal elements, and that's why kappa coefficient gives you very good accuracy. So they monitor more on, they have more confidence on kappa than on overall accuracy. So this is all about for today's lecture. I started just to give you again flavor of understanding what is image mathematically in the form of row and column and the digital number. That is very, very important. And then the resolutions of the images. In the remote sensing, you have resolution means to distinguish the object with respect to the spatial, that is distance, with respect to spectral means wavelength, with respect to shades, that's radiometry, and with respect to time, that is temporal. So there are 4 types of resolutions in the remote sensing. That's very, very important. And then I just talked about the separability analysis, which is used to decide for a given number of classes how many bands we should use to process. Do we require all the bands or minimum number of bands are enough to be considered for classification of the given classes? The separability analysis, if you see, it works on training data, and then we can find out how many optimum number of bands are required to classify the image. This exercise of separability analysis is very, very important when we go for hyperspectral images. There are 100, 200 or 400 bands image, and there we don't require all the bands because the computation time is very, very large. So we can cut down the computation time, and that way we can go for separability analysis. And then I talked about the definition of digital image classification and the 2 methods, supervised and unsupervised. I talked about the unsupervised means we are not providing the training data. Algorithm is doing the iterations, assuming the variables, refining the variables of the algorithm, and doing the final doing the clustering and generating the clusters. In the clusters means the labels are missing. They just have the class 1, class 2 information, or label 1 or label or cluster 1 and cluster 2. We do not know what is cluster 1 or what is class 1 in the output. For supervised, we provide the training data, and that's your samples of training to calculate the parameters of the algorithm in these statistical pixel-based parametric classifier. We generate the mean and the variance covariance parameter, or sometimes minimum and maximum parameter, or mean and standard deviation, depending upon which algorithm we are using. We mentioned for unsupervised, we have to use only C-mean algorithm. For supervised, we can use 4 well-established statistical algorithm, that is C-means, or minimum distance classifier, or Mahlanov-Bayes classifier, or parallel-piped classifier, or maximum likelihood classifier. And I have explained the mathematical concepts, how they work. And then in the lastly, I talked about the thematic map. If it is generated by these algorithms, we have to do accuracy assessment of this thematic map. And for that, we have to go for confusion matrix and error matrix. And we can generate, once we generate when we decide and get the testing pixels, testing samples, using the testing samples, we can create the error matrix or confusion matrix. And then we can generate 4 parameters, that is user accuracy. User accuracy means how correctly the testing sample is on the classified map. Second is producer accuracy, how correctly the testing sample is on the reference map, and we can get the user accuracy and producer accuracy for all the classes. Then overall accuracy of the full thematic map and the kappa coefficient. Overall accuracy and user and producer accuracy is in percentage. Kappa coefficient is 0 to 1 value in the range. And we can also get the error of commission, that is error in the user accuracy, and error of commission, error in the producer accuracy. User and producer accuracy we can get for all the classes.